Maxwell's equation. Magnets. Today, magnets and magnetic materials are everywhere. We find them in VCRs, audio cassette, ATM and credit cards, audio headsets, and even in inks for paper money. More important, the modern electronics industry, as we know it, including the music and information domains, will not exist without magnetic materials. Gauss law for magnetic field. We look these magnets. Iron filling sprinkled around such magnets tend to align with the magnetic field of the magnet, and their pattern reveals the magnetic field line. The clustering of the lines at the ends of the magnetic suggests that one end is a source of the lines, the field diverges from it, and the other end is a sink of the lines, the field converges towards it. The simplest magnetic structure that can exist is a magnetic dipole. Magnetic monopoles do not exist as far as we know. This is a magnet. You have North Pole and South Pole. If you cut into three, each three has North Pole and South Pole. Okay, you never find magnetic monopole, North Pole alone. The fundamental magnetic dipole in nature, the one responsible for the magnetic property of dark matter, is that associated with the electron.
This bar magnet has a north pole on one end and a south pole on the other, as shown by this compass. If we break the magnet in half, will each side contain only one magnetic pole? Each half of the magnet still has both north and south poles.
Gauss law for magnetic field. This is a flux for magnetic field around a Gauss closed surface. We compare the electricity. Okay, this is Gauss law tells us this is integration for the closed Gauss surface is equal to Q enclosed over epsilon 0. Okay. Q is the net charge inside this Gauss surface. But for magnetic field, it's always equal to 0. Gauss law for magnetic field is a formal way of saying that magnetic monopoles does not exist. The law asserts that the net magnetic flux phi b through any closed Gaussian surface is 0. The simplest magnetic structure that can exist and thus be enclosed by Gaussian surface is a dipole, which consists of both source and a sink of the field lines. You look at all these closed circle. The net flux is 0. By convention, we call source the north pole of the magnetic, and the opposite end the south pole. And then we see that magnetic with its two poles is an example of a magnetic dipole. Magnetic field lines are closed loops is different, okay, from electric field lines. Induced magnetic field. A change in magnetic flux induces an electric field, and we end up with Faraday's law of induction in the form. Change magnetic field flux speed changes, you produce electric field. That's Faraday's law. Can a changing electric flux induce a magnetic field? The answer is that it can. So, compared to this one, we find this one. Okay, any different? Yes. See, this minus sign, this positive sign. We have a coefficient mu0, epsilon 0. And this we know later, mu0 epsilon equal to 1 over c squared. So the difference is sign and coefficient. Okay. We will prove it later. That's called the Maxwell law of induction. But this side on the left side is a little bit familiar. Did you see that before? Yes. Yes. This is a flux speed. What is this? This is equal to mu I0. This is Ampere's law. So both this one we combine together and we see, is two terms. Okay, one is Ampere's law, one is Maxwell's law. So we call it Ampere-Maxwell's law. Now look at this. This is a circular plane, parallel plane. You have a current inside. The current in, you have a charge, positive charge accumulated here, and a negative charge here. So inside this circular plane, you have an electric field. The direction is from this to this, from left to right. Okay, it's uniform. We have 2 points. Point 1 is inside this plane. Point 2 is outside this plane. If you look from the left side, we will see the electric field inside is leaving you. This one, okay, is leaving you, uniform. And based on this Ampere-Maxwell equation, when I changes, you have flux E changes. Because of the electric field change induced magnetic field, we have 2 points. Let's see the point 1 inside this plate. Okay, we make a circle. Okay, we circle. We use this formula. See, the flux E changes as time. Okay, then you will induce B. All right, and inside this one we don't have net charge. This is 0. Okay, okay, and we see when this one increase, according to the Gauss law, we find it's not against it. So this currents go this direction, so you have a B. Same thing like increase. Okay. A magnetic field is set up by this changing electric field, both inside and outside. Okay. Let's compare electricity and magnetism. This is Faraday's law. Okay, you have minus sign. If the B increase, then we have E is produce induced current always against a change. Okay. Now, this is the Ampere-Maxwell equation. Okay. This is minus sign. This is positive sign. So, if you take a circle which passes point 1, okay, this B is positive, this E is negative, the different direction. Okay, they don't against the change. Okay. Example: a parallel plate capacitor with circular plates of radius r is being charged as in Fig A. As before, this is derive an expression for the magnetic field at radius r from case r smaller big R. This is point 1. R smaller than big R. This is big R. Now we see that's what this R is smaller. So we make a circle passing through this one. This is R, a small R. Okay? And since the net current is 0, so we use this Ampere-Maxwell equation. This is 0. Okay, we find this one. On the left side, this is B by symmetry reason is everywhere in the same magnitude along this curve, but different direction, along the tangent direction, right? So the B dot ds is always equal to B 2 pi r. The S is 2 pi r. And this one is mu 0 epsilon 0 phi e. Look at the phi e. Phi e is E uniform multiplied by the area is pi r squared. Okay. And this is nothing to do with time t, so we take it out. This is this one, all right? So finally we find the B equal to r cancel the 1/2 mc di dt. We get this answer. The B depends on how E changes. B. Derive an expression for the induced magnetic field for the case R larger than R. It's point 2, larger than R, big R, okay? Now, a little bit different. I equals 0, 2. So this equation still become this one. This is 0. Now we look at this one. Question is phi e. This is the same side. B is parallel to ds. So B dot ds equal to B ds. And B is constant. Take out. You take the B 2 pi r. The circumference of the circle. I'm sorry, this one. Okay, this one. And then we see the phi e. Now, in this case, it's different from inside, because whatever r changes, the electric field only limited here. So the phi e equal to E pi r squared is constant number, as long as E is constant, okay? This is constant number, nothing to do with the r. Okay, then we get this one, B. Displacement current. We rewrite this Maxwell equation, and with the color, we see they have a mu 0, mu 0. If you compare the two terms on the right side of the equation, you will see that the portion epsilon 0 d phi e dt of the first term must have the dimension of a current. This is a current. This should be the same dimension. Current. In fact, historically, this portion has been treated as being fictitious current called a displacement current ID. So we rewrite it. It's simple. It's ID equal to epsilon 0 d phi e dt. We define this one. And then this equation can be rewrite simply. So B dot ds integration equal to mu 0 id plus I net. We look at this case. You have a charge alternating current get in. So this is a positive charge, and this is negative charge. Okay. Inside you have an electric field from left to right, and we see we have displacement current ID. Let's again focus on the charging capacity with circular plates. Okay. The real current I, that is charging the plates, changes the electric field between the plates, because more electric on this side and a larger E. Okay. The fictitious displacement current ID between the plates is associated with a changing electric field E. Let's just relate these two currents, ID and I. Look at this conducting current I. This I is related to the Q here, as dQ dt. Look at this one. This displacement current definition, okay, already have it. Epsilon 0 d phi e dt. Okay. Now this is E related to sigma, the charge units, And the sigma equal to, sigma is the charge per unit area. So it's Q over A. Q is the charge on this one. A is the area of this circular plane. And so the Q equal to epsilon A E. And I is dq dt. So equal to epsilon 0 A dE dt. And we look at displacement current. By definition, it is epsilon 0 d phi E dt. Okay. And what is d phi E? D phi E is EA. This is E uniform plus A. The A is nothing to do with T, so take it out. Becomes UD equal to epsilon A dE dt. We compare to this current conducting current, I equal to epsilon A dE dt. They are exactly the same. Okay. The conducting current I is not continuous across the capacitor gap. However, the displacement current ID in the gap is exactly to be I. This retaining the concept of the continuity of current. Find the induced magnetic field. We want to find the induced magnetic field inside this one. We can see ID is equal to I, exactly. So the B inside should be this one. If we have learned it before, right? I write it different from textbook. This is R over big R squared. I divided into two terms. This term is the magnetic field on the ring of this capacitor. This is maximum B. Okay. Also, from outside is the minimum distance, also the maximum D. Okay. And inside, I put the ratio R to big R. Right? And outside is this one. So we know the biggest is B is mu 0 I 2 pi R. Because this R is the largest one. So this one is smaller than this one. This is biggest B. Okay. Inside, I put the ratio. Okay. We can find the direction of the induced magnetic field produced by a fictitious displacement current ID, as shown in the center of the figure. This one. Okay. Same thing. We look takes ID as a real I. Can find direction. Yeah. Sample. The circular parallel plate capacitor is being charged with a current I. Question A. Between the plates, what is the magnitude of B dot ds integration in terms of mu 0 and I? At the radius R equals big R over phi from their center. We know this one is equal to mu 0 ID plus I net. In our case, I net is 0. Okay. And then, so there's a mu 0 ID XC, right? And we want to find this one, okay? What is ID? Now, depends on the location. ID is I, totally is I. And for our location R, big R over phi, the ID net is divided ID over I pi R. This is a current per unit area, and in our case the locations are the area whole circle is pi R squared. So this one we put R equal to big R over phi, and we get this ID equal to total I over 25. Then we put one side. That's it. That's it. We find the B. We find the B location. In terms of maximum induced magnetic field, what is the magnitude of the magnetic field induced at R equal to R over phi inside the capacitor? Now we know this one. This one, we do the integration because of symmetry, B is always along the tangent. So B dot ds equal to B ds. So this one equal to B 2 pi r. And on the right side, we have mu 0 I. This is I r squared over r squared. It's mu 0. Okay. So BR equal to mu I over 2 pi r over r inside. Okay, inside. And you put r equal to half r equal to BR. And we are asked to express this BR in terms of the B maximum. We know the B maximum is mu 0 I 2 pi r. This is maximum. In outside, it's outside, this is r, the smallest. So this is the biggest. So this is maximum. Okay. So in terms of this one, and then we find this one. So B, this one half. So B equal to B maximum over 5. That's the answer. Maxwell equations. Gauss law for electricity. This is net charge inside the Gauss surface. This is related net electric flux to net enclosed electric charge. Gauss law for magnetism. B dot dx equal to 0. Related net magnetic flux to net enclosed magnetic charge. That means no monopole magnet. Faraday's law. Related induced electric field to changing magnetic field. Ampere-Maxwell law. Relates induced magnetic field to changing electric field and to current. Notice, these 4 formulas written on the assumption that no dielectric or magnetic materials are present. These 4 equations explain a diverse range of phenomena, from why a compass needle points north to why a car starts when you turn the ignition key. They are the basis for functioning of such electromagnetic devices as electromotors, cyclotrons, television transmitters and receivers, telephones, fax machines, radars, and microwave ovens. Maxwell's equations are the basis for which many of the equations you have seen in electricity and magnetism can be derived. They are also the basis of many of the equations you will see in optics, as well as such optical devices as telescopes and eyeglasses.